Hello everyone, welcome to my YouTube channel. In previous 8 videos we have discussed a lot about partial differentiation. Now in this video I am going to discuss an important theorem on partial differentiation which is called Euler Theorem for homogeneous function. So before we discuss Euler Theorem for homogeneous function, first we have to know what is the meaning of homogeneous function. So first we define homogeneous function, and the definition of homogeneous function is if fxy be any function of two independent variables x and y, then it is said to be a homogeneous function of degree n if the sum of power of x and y in each term is same and it is equal to n. If the sum of power of x and y in each term is same and equal to n, then the function f of xy is called homogeneous function of degree n. For example, consider this function of x and y is a0 x power n plus a1 x power n minus 1 into y plus a2 x power n minus 2 into y square plus so on an y power n. Here a0, a1, a2 and an are constant. Now we observe that in first term the sum of power of x and y is absent, so y power 0 and x power n, so total sum of power is n. In second term the sum of power is n minus 1 plus 1 power of y, so total sum of power is n. In third term the sum of power n minus 2 plus 2, so the sum of power of x and y is n, and so on. And finally in last term the sum of power of x and y is x power 0 and y power n, so total sum is n. So in each term the sum of powers of x and y is equal and it is equal to n. So this function f of xy is homogeneous function of degree n. Further, this function can be expressed as we take x power n common from this expression, then we have function of xy is equal to x power n common, then a0 plus a1 into here x power n common, then we have x power minus 1 which is equal to 1 upon x, so y by x, plus a2 here x power n common, then we have x power minus 2 which is 1 upon x square, so y square by x square, we have y by x whole square, plus so on. Here x power n is absent, so we divide by x power n, then we have y power n upon x power n which become y by x whole power n. So homogeneous function of degree n can be expressed as function of xy is equal to x power n into function of y by x. Similarly, if we take y power n common from equation first, then we have function of xy equal to here y power n common, then we have a0 x by y whole power n plus a1 x by y whole power n minus 1 plus a2 x by y whole power n minus 2 and so on plus an. So further the homogeneous function of degree n can be expressed as function of xy is equal to y power n into function of x by y. So this is the definition of homogeneous function. A function in which sum of power of x and y in each term is same and equal to n, then the function is called homogeneous function of degree n. Now we discuss Euler Theorem, which states that if z equal to function of xy be a homogeneous function of x and y of degree n, then x into del z by del x plus y into del z by del y equal to nz. That is, the partial derivative of z with respect to x multiplied by x and the partial derivative of z with respect to y multiplied by y, then their sum gives n times z, where n is the degree of homogeneous function. So this is the statement of Euler Theorem. If z is homogeneous function of degree n of independent variable x and y, then x del z by del x plus y del z by del y gives n time the function z. Now we are going to prove this theorem. So since fxy, z equal to fxy is a homogeneous function of degree n, then we can write homogeneous function of degree n as z equal to x power n into function of y by x, as we discussed in the previous definition of homogeneous function. Now we differentiate equation first with respect to x partially. We get del z by del x, partial derivative of z with respect to x, del z by del x equal to, here we apply u into v formula for differentiation. So derivative of x power n with respect to x is n into x raised to n minus 1 multiplied by function of y by x plus multiplied by x power n, and derivative of f of y by x is f dash of y by x multiplied by partial derivative of y by x with respect to x. So with respect to x, y is constant and derivative of 1 upon x is minus 1 upon x square. So this is del z by del x, partial derivative of z with respect to x. Now we multiply equation second by x. We get x del z by del x equal to, here we multiplied by x, then we have x power n, then we have n x power n into function of y by x. Here positive, negative, negative. This when we multiply x, we have 1 upon x, then x power n upon x gives x power n minus 1 multiplied by y multiplied by f dash of y by x. So this is the value of x del z by del x. Now we differentiate equation first with respect to y partially to get del z by del y. So differentiate equation first with respect to y partially. We get the partial derivative of z with respect to y is del z by del y. Here with respect to y, x power n is constant, so we have del z by del y equal to x power n constant. Now the derivative of f of y by x with respect to y, we have f dash of y by x multiplied by partial derivative of y by x with respect to y. So with respect to y, 1 upon x is constant and derivative of y with respect to y is 1. So we multiply it by 1 by x. Now multiply this expression by y, we get y del z by del y equal to x power n upon x gives x power n minus 1 multiplied by y into f dash of y by x. So this is the value of y del z by del y, the partial derivative of z with respect to y multiplied by y. Now we add equation third and fourth. Then this expression is cancelled and we have x del z by del x plus y del z by del y equal to, this expression is cancelled, then we have n into x power n multiplied by function of y by x. Now this x power n into function of y by x, this is what? This is our given function z. So we have nz. So this is the proof of Euler Theorem, that if z is homogeneous function of xy of degree n, then x del z by del x plus y del z by del y gives n time z. Similarly, we can extend this Euler theorem for 3 variables, 4 variables, 5 variables. Suppose z is homogeneous function of degree n of 3 variables x, y and t. Then Euler theorem can be expressed as x del z by del x plus y del z by del y plus t del z by del t gives n times z, and so on. So this is the proof of Euler theorem. Now we take an elementary example on Euler theorem. So the question is, if u equal to sine inverse of x square plus y square upon x plus y, then prove that x del u by del x plus y del u by del y is equal to tan u. So this expression x del u by del x plus y del u by del y is of the form Euler theorem. So here we apply Euler theorem. Given u equal to sine inverse of x square plus y square upon x plus y. Therefore, sine u is equal to x square plus y square upon x plus y. Now, from numerator we take x square common and from denominator we take x common. Then x square by x gives x multiplied by, after taking x square common from numerator we have 1 plus y by x whole square in numerator, and after taking x common from denominator become 1 plus y by x. Therefore, sine u is equal to x into function of y by x. So this is the expression of homogeneous function of degree 1. So sine u is a homogeneous function of degree 1. Suppose this is v. We denote this function by v. So v equal to sine u. V equal to sine u is a homogeneous function of degree 1. Therefore, by Euler theorem, since v equal to sine u is a homogeneous function of degree 1, therefore by Euler theorem we have x del v by del x, because v is homogeneous, so we apply Euler theorem on the function v. So x del v by del x plus y del v by del y equal to 1 time v, as v is a homogeneous function of degree 1. So this is the expression of Euler theorem for the function v of degree 1, x del v by del x plus y del v by del y equal to 1 time v. Now the value of v is sine u. So we have x del by del x of v is sine u, plus y del by del y of v is sine u, equal to 1 time sine u, that is sine u. Now we differentiate sine u with respect to x partially, and then here we differentiate sine u with respect to y partially. We get x into derivative of sine u is cos u multiplied by partial derivative of u with respect to x, so del u by del x, plus y into derivative of sin u is cos u multiplied by derivative of u with respect to y partially is del u by del y equal to sin u. Now we take cos u common, then we have cos u into x del u by del x plus here cos u common, so y del u by del y equal to sin u. Now we transfer cos u in right hand side, then we have sin u upon cos u which become tan u. So we have x del u by del x plus y del u by del y equal to tan u, and this is the required proof. So this is how we apply the Euler theorem for homogeneous function. In next video we will take few important examples on Euler theorem for homogeneous function. So see you in next video. Thank you.